So, during the session, and we'll have a talk on solving the Schrödinger equation in configuration space with machine learning. Floor is yours.
Thanks, Dan, for the introduction. So, my name is Basile Herzog. I'm a PhD student in the Laboratoire de Physique et Chimie Théorique in Nancy, under the supervision of Sébastien Lebègue and Dario Roca. And I will present you this work, which is half of my PhD. So I will begin by a very pedagogical introduction to generative machine learning. I will go specifically into the restricted Boltzmann machine model and see how we can use it to learn a probability distribution and sample from it in the famous handwritten digit problem. And I will then introduce shortly the configuration interaction theory and what are the shortcomings of it and how we can some approaches to resolve it. And then I will present my method, the CIPSI method, to use generative machine learning to select important configuration in the CI problem. So generative machine learning. So this is a photograph from the famous website thispersondoesnotexist.com. So it is a website where the generative adversarial network has learned the probability distribution of the joint probability distribution over the different pixels of thousands of images of human faces. And we are then able to sample new faces that doesn't exist from this distribution. But we will not talk about generative adversarial neural network, but more about energy-based model, which are all the information-based models that come from statistical physics, in which you define energy function E, which is a function of the data, the training data sets, and from the model parameter, and in which you want to make to associate the lowest energy to the most probable configuration in your data set, and reciprocally as in a physical model. More specifically, the restricted Boltzmann machine is this model that is quite old now. It's a very simple model with one visible layer V, which take binary inputs, and one hidden layer H that take also binary inputs, and that will encode the latent variable of your problem. You have biases vector A and B as a model parameter, and a matrix weight W between both. So you can define this energy function of VH, so configuration of the model is the set of one vector V and one vector H, and of the model parameter ABW. So this is a simple linear combination. And you can define a probability over, for example, here the probability for configuration V will be the sum over all possible configuration H of this Boltzmann like probability, and the name. Now I will go into this study case, which is actually I took Pickle Station in my master study. So this is the famous digit data set where you have a 28 by 28 pixel. You can flatten into a binary vector, a set of binary vector V. And for the purpose of this demonstration, I only take the digit 5. It's more relevant for the following. And so the goal is to learn the probability distribution, the joint probability distribution of all the value of all the pixels. So in order to do that, we first need to see how we can sample with our model. So this is, we will use the Gibbs sampling algorithm, in which you first sample an input vector V with uniform probabilities. So you have a probability 1/2 to have either 1 or 0. And then you use the probability of your model to sample the value of the hidden layer H according to the probability that the HI are equal to 1 given the value of the visible layer, and you go backward to sample again the visible layer, and you can do that for a certain number of steps, and at the end you keep the last vector v and h, that is the sample that you extract from your model. So this is basically Markov chain that is written here, and it is graphically equivalent to the Metropolis algorithm, but in the Metropolis algorithm you will sample both the visible and hidden layer and accept with the Metropolis. And here it is the same, but by sampling only the visible given h and then the hidden given v, you have the Metropolis algorithm, but with a 0 rejection rate. Now to train the restricted Boltzmann machine, you can use the contrastive divergence algorithm by Hinton, in which the goal is to maximize the log likelihood of your dataset given the model. So this is unsupervised learning. You want your trained model to produce a sample that will look like the training dataset that you used in the training. So to do that, you can derive the log likelihood of your model, and you will have those nice expressions that are differences between average over the data and averages over the model. So, for example, the averages of the VK over the data is simply your training dataset, and the averages over the model is visible configuration that you obtain through Gibbs sampling. The the averages over the data for the hidden layer are not really averages over the data. It means that you take as the first step of the Gibbs sampling your training dataset for the visible layer. Now you cut your training dataset into mini batches of size NV, and for each mini batch, you sample visible and input layer according to Gibbs sampling. You compute your averages, and you update your parameter accordingly to those expressions with a learning rate epsilon. And once it has been trained properly, when you perform Gibbs sampling from your model, you will obtain those. So this is the first step with the uniform probability for the visible layer. So it's a white noise, and already in the first step of Gibbs sampling, you can see pattern varying. And on the second step, you have a 5. So the convergence is also really fast. So that's an advantage of Gibbs sampling. Now the configuration interaction theory. So it is a post-Hartree-Fock method in which you start from your mean-field solution Hartree-Fock, and you write your expansion of your Hartree-Fock Slater determinant and all possible excitation upon your Slater your Hartree-Fock Slater determinant. So if you want the full CI solution, that is all the possible determinants you can have in the CI. So this is basically a combinatorics problem. It's how to choose an electron among your 2k spin orbital. And for example, for a simple molecule like nitrogen CCPV basis, you already have 10 to 12 determinants, which is here I use the fact that it's closed shell, so it's still not so big. So for open shell system, it's bigger. And so it is numerically infeasible for most realistic systems. So here I want to show, so this figure is extracted from the full CI solution of the water molecule in the 6Q1G basis set at equilibrium geometry. So I take the full CI solution and I order every coefficient in the expansion by the absolute value. And I plot it in a logarithm scale. So you can see that only Q100 of the first 1,000 configuration contains almost 99% of the full CI energy. So this means that you really doesn't need to solve the full CI problem in order to have very accurate results. This is a characteristic of the equilibrium geometry, as you have few static correlation, but the form of this function will be quite the same even near the dissociation part. You have also this important part that if you have two Slater determinants that differ by more that you are the corresponding Hamiltonian matrix element will be equal to 0. You have also spatial and spin symmetry to take into account that will create 0 element matrix inside your Hamiltonian. So the matrix is really, the Hamiltonian matrix is really sparse. So it encourages you to use selective iterative approaches, where at each iteration you will only consider the set of single and double substitution and keep only those that are important. So for example, there is the famous CIPSI algorithm in which you start from, for example, R3 fork, you generate all the single and double substitution from R3 fork. And then you apply perturbation theory to select the most important one. Diagonalize, you can prune the wave function and you go back to the step 2 and you go like this. So this is a very efficient algorithm, it converges very fast, but it has a overall complexity of O of n third with the number of determinants at each iteration, because the number of single and double substitution scale has n squared, and then you have to apply perturbation theory, which typically scale as n, so O of n3, so it is numerically inefficient, but the convergence is really fast. Another approach that is more interesting to me is the Monte Carlo CI, in which you do the same. You start from a given wave function, and then you will randomly generate your single and double substitution. And then you will diagonalize this new space and go back to 2. So the scaling here is when you generate your new substitution, you will typically try to generate a number of determinant that is proportional of the determinant currently inside the wave function. So the scaling is O of n with the number of determinants. So it is much more efficient numerically, but the convergence is much slower. So in the CIGen method, I will try to use generative machine learning to enhance the Monte Carlo procedure. So I first need the data set to train my data on, my model on. So for a given wave function Cn, that is the sum of Slater determinant with coefficient Ck, I want to learn the probability, this probability Q, which is the bound probability in my truncated Hilbert space. And so I will create a fake data set of n. Typically, I use the 50,000. I will create 50,000 Slater determinants in which the frequency of the determinant are taken from this distribution that I want to learn. Now, this is just to say that Slater determinants are already binary vector, which only tells the occupation or unoccupation of the spin orbitals. So it is already made for restricted Boltzmann machine model. And so I have, this is the same slide I have earlier. I encode all my Slater determinants into the visible layer. And I can define this energy function that I put in quote because, of course, it is not an energy at all. I can define this Boltzmann-like probability and train my model. There is little subtleties that in the traditional GIP sampling, for example, for the digit, I don't care about the number of 1. But here I want to have a number of 1 that is equal to the number of electrons. And I'm only considering closed shell system here. So I also want a number of spin up electrons that is equal to the number of spin down electrons. So I use the tower sampling algorithm, which is a rejection-free discrete sampling algorithm, which is very simple. So in this ladder, the rectangle represents the probability of occupation on the visible layer, so the probability that VI equals 1/h. and the area of the rectangle is proportional to this probability. So if I draw a number inside this ladder, it will arrive into an orbital with a probability that is proportional to the probability of occupation. So I can sample with no rejection. So choose an orbital to occupy. Then I put this probability to 0 and continue the process until I have the number of electrons that I want. I do that separately for the spin up electron and the spin down electron. And now the CIPSI algorithm is like the one before. So I start from the CIPSI wave function in my case. I diagonalize the wave function. I print the determinant whose coefficients are under threshold min. And then I train my RBM on the remaining determinants, from which I exclude the Hartree-Fock determinants, since it represents usually 0.95 of the probability. So I don't want to, it's not interesting to keep it. And additionally, I'm interested in the correlation energy, which is defined as the difference between Hartree-Fock and the Fourier wave function. And then I will generate a number of determinants proportional to the one that I currently have in my wave function. So typically fgen here, I used 2. So each iteration, I try to generate twice the number of determinants I already have. And I go back to 2 until convergence. So I have a 2-way of each function generation, but with only one step. I don't try to obtain converged determinants, because determinants will be determinants that I already have in my wave function if the learning is properly done. So I use only one step to have out of a group, out of equilibrium points. So determinants that use the learning but are not exactly the same that I should learn from. And then I will keep the proposed determinant if it is not already in my wave function, if it respects the point group symmetry of the problem, and if it belongs to the set of single and double expression of the configuration of the wave function. So this is the result with this algorithm for the water and susceptibility databases. So I can obtain chemical accuracy with 11 iterations, selecting 1 million determinants out of the 40 million in the end. And the black curve corresponds to I say random generation. It means I will populate my orbital with a probability 1. So it's a uniform distribution for the generation of determinants. So basically, the difference between those curves are the result of the learning. So I'm already happy with this result, since it showed the proper learning of the methodology. Now I want to, so CIGNSD is another approach where I directly generate the single and double excitation. So this is not only for numerical efficiency, I will see. So let's say that I start from a state where I only have 2 determinants in my wave function. And from those 2, there are 4 that are directly connected by single and double substitution. And so let's say the left one is connected to the tree left above, and that the right one is connected to the tree right above. So this means that the 2 middle ones are connected to both. And so if I randomly generate with a uniform probability single or double substitution from those 2, I will obtain those 2 with more probability than the 2 on the extremity. So the thing is that when we are using Monte Carlo approaches, we generate a subspace of the single and double substituted space, which means that we can miss matrix elements needed to evaluate correctly the coefficients associated with those determinants at the diagonalization step. So if I have, if I select more connected determinants, I will be able to select a subspace that is more connected, so I have more information to decide if they are more important or not. And this is at the heart of the Monte Carlo CI procedure, which already makes it quite efficient with purely random generation. So in this case, to generate the single double generation, I select a random configuration VBAR inside my current function, and I perform independently a Gibbs sampling to obtain final probability of occupation from my model. And I construct a transition matrix from occupied orbital in my selected determinant VBAR to unoccupied orbital in the same determinants. So the transition matrix is defined here. So basically it says that the most probable occupied orbital is to be occupied by my model, the less probable it will be to leave it, and the most probable the unoccupied orbital is to be occupied, it will be more probable to arrive there. And of course,
Sorry to interrupt you. There is a parasite sound. We cannot hear you. There is a terrible sound which prevents to hear the speaker. There is a permanent sound. Yes, it's off.
It's okay?
Yeah.
Okay. So you heard nothing before?
No, almost nothing. Sorry about that.
Yeah, so this line is the one to remember. So for the, okay, so I start from a guess wave function here, from which I create a training data set inside which the determinant will match the frequency of my guess wave function. And I can learn the probability, the joint probability distribution over the occupation of the spin orbital thanks to the RBM model. And I will then be able to sample new Slater determinants according to this probability. So new probable determinants according to this model. I will then diagonalize the new basis and repeat this procedure until convergence. So I hope to have shown you that a generative model can be used to solve the Schrödinger equation by sampling the Slater determinant that contribute the most to the wave function. numerical application show that is already competitive with previous Monte Carlo approach of machine learning representation on ZATs. I submitted the project and the preprint is available on arXiv. In the future, I could envisage to directly learn the symmetry, for example, the spatial symmetry or the spin symmetry, and to change the single double generation algorithm because there are a lot of ways to make that. And so this was devised for configuration interaction algorithm, but theory, but it's also very suited to treat, for example, Heisenberg Hamiltonian. And after that, I'd like to acknowledge my people. So my group leader are Dario Roca and Sébastien Lebec. Bastien Cazé is my collaborator, and it will speak of a project that is quite similar. Also, Maurizio Chagas da Silva that helped me discussing, and Anthony Shemama that gave me a lot of help with the quantum package. In the diagonalizers, for diagonalize the wave function, I use the code quantum package that is his. And I have still a bit of time, but no, okay, let's finish that. Thanks for your attention.
So I wonder, did you compare your method to the CIPSI method?
Yes, I did. The thing is that it is hard to compare because in the CIPSI algorithm, they will construct all possible single and double generation determinants, and then they will decide which one is important. So it's a very deterministic model where you consider every possible case. That's why it is, yes, it is of course more efficient than my model. Actually, my model has a convergence curve that are intermediate between the CIPSI and the Monte Carlo.
Okay. But in terms of accuracy, you get the same one.
Yeah, of course, I get the same one.
Yeah. And so, I mean, by the comparison, it would be also nice to look at the selected configuration at every step to see if your method, I mean, follows the same path as the CIPSI, because, I mean, as you said, it's deterministic in CIPSI, but is it the right way to do it? Does your model follow the same path somehow? Or? I mean, not exactly, because as you said, the convergence is different, but maybe it follows somehow around this path, and that's why it's
yes, at each step, yeah, the path is the same, but I will necessarily miss some of important single double substitution so that I will obtain later in the process. So, but in the Monte Carlo also, in the standard Monte Carlo, it is the same. You will follow the same path, but you will have to find some important one that you could have found since the beginning later, because at this point they were not important enough to be seen.
But no, I mean, if I understand correctly, in the Monte Carlo, I mean, at the end you arrive to the same place, right? But the paths are completely different because in Monte Carlo you just go all over the place and try to get to the final position, right?
That's why I say
while
that it is
in CIPSI it's the path is clearly defined, like you have the map and you know you have to go that way. And yeah, I wonder in your case if you follow really, I mean, you take this map and do you have the same?
But to be honest, no, I didn't. I don't have this kind of analysis step by step, and it's hard to do because in CIPSI algorithm you can really construct a map that is you have artifact, single, double, triple, quadruple, and you go like this. It is very deterministic. In my case, I cannot use this single, double, triple, quadruple, because at each step I'm with my wave function and I construct a single, double from this one.
Okay, I'm not sure. But
so yeah, it should be different. It will be less efficient, of course.
Okay.
We have, yeah, go ahead.
Yeah, thank you for your talk. Some of my work, but I want to follow the discussion about between CIPSI and your method. So you're saying CIPSI there's less iteration, but in terms of computational time, I guess your method is more efficient.
Yes, the computational efficiency of that's why we use Monte Carlo, because Monte Carlo are much more efficient numerically, but the convergence is much slower. Okay. So the idea is that in the deterministic procedure of the CIPSI algorithm, you use physics in perturbation theory. You use perturbation theory to decide what's important. While in Monte Carlo, you go blind, but you will, with some steps, arrive at the same conclusion. And here it is a bit hybrid, because the idea that the neural network should learn some kind of physics. I don't know how to define learning physics in this case, but it learned clearly something. And so it has still the advantage of a Monte Carlo procedure, so reduced computational cost, but with some insight of the correlation that exists between the different states of determinants.
Okay, so that's clear. So right now you're doing that only for the ground state. Can you do that also for excited state? I guess yes, but I think your selection will be slightly different, because probably you need both to calculate both states, the ground state and some kind of excited states. Is it possible right now?
From my understanding, I just need in the diagonalization procedure to take one more step. So yeah, it should be possible.
Yeah, but in terms of the relevant determinant, it will be, yes, the time of selection will be not exactly the same.
And I didn't try yet, but that was one theory.
Yeah. And another thing, which is also the case in CIPSI, when you trace a curve like dissociation curves, you end up with different kind of determinant between, let's say, the optimal, the equilibrium distance and the dissociation. Yeah. So in between, you will get some kind of not continuous curves. Do you have this problem, or you can really push the convergence so that this problem is disappear completely? So your number of excitation, number of determinants will be different from one point in your curve to another one. So this means that you're going to have some kind of non-continuous curve, dissociation curves.
No, it only means that I will have a non-continuous curve in the number of determinants that I need to have to obtain proper energy. Yeah, because
but if you plot the curve, you will have some kind of small jump between one point where you have the same determinant and another one when you add more or less.
But
that's this problem in CIPSI.
But there is no transfer learning here. So for each point, I do a completely separate calculation, and I stop when I have the convergence that I with some convergence criteria. So it must go inside let's say if I push the convergence hard, I will obtain something that is quite close to full CI value, where there is not this kind of problem that you can have with CISD or this kind of.
Okay, thanks.
But the number of determinants, you have to have this kind of convergence between the equilibrium value and the dissociation. I have like 10 times more determinants, yes, because there is it is much more correlated, and R3 fork is only, I don't know, 0.25, and I need to take into account a lot more determinants.
Can you start with some multi-reference calculation instead of artWIFOC?
I start
right
with
now?
CISD. I start with CISD.
Yeah, but let's say CASSCF calculation instead of.
Yeah, I guess it should. So, but I was also thinking of doing I can't remember the name, where you enforce the total symmetry of your guess wave function. But no, I didn't try that.
Okay, thanks.
Oh, beautiful talk. I wonder why you don't use the information from the previous step in your curves. So why do you start from each point from scratch?
No, I totally agree. I should do that. That's the goal in the future. Yeah, just for the purpose of this. As I took only, I took one that were quite far apart. I didn't do the full. I didn't put the same number of points as I do in the full CI curve. But if I would do a very close point, I will do that. Yeah, sure.
Thank you.
If any other question? Nothing online. So I'll have one or two. So do I get it right that in general, the bottleneck in the end is always the diagonalization, or is that not the case? So because we're discussing sort of efficiency of using your approach versus CIPSI, and that this is the bottleneck, the diagonalization.
Yes, yes.
Yeah, okay.
When you approach convergence and you have millions of determinants, that's the most consuming part.
Okay, cool. And then another question is, so you're always plotting curves based on the energy, and it's kind of the metric for you in a way. But have you looked at, for example, taking a wave function generated by your method and say the one from Monte Carlo CI or CIPSI, and sort of taking wave function at the same, looking at how many determinants?
Yes, I did that. I don't show this curve. I did a curve where I take the full CI reference.
Yeah.
And I take different threshold criteria for the number of for the coefficient. And I can compare the full CI curve with mine. I didn't do it for CIPSI, but it was just for compare with full CI reference. And yes, to see that it's superposed quite well. So the number of determinants that are kept to have a certain energy and a certain threshold match quite nicely. It's more the number of steps you need to arrive there.
Okay. So if you think of all these as a sort of compression of the full CI, then effectively what you're saying is that the compression efficiency is actually comparable in all of these, and it's more about how quickly.
Yeah.
Cool. Thanks.
A question about your comment on diagonalization.
Yeah.
I guess you're using some kind of Davidson or Lanczos technique.
So I use quantum package, so that use Davidson.
Yeah. And so are you using the guess of the previous iteration to converge your eigenvalue with Davidson or not? Because that would be will help a lot.
Yeah, no, I didn't do that.
Yeah, because that's in a few iterations you get most of the wave function. So then in few Davidson iteration, you would get.
No, sorry, yes, I do that. Sorry,
you do that. Okay. Okay, so that's clever. Okay, thanks.
Any more questions? Looks like not. So let's thank Basil again. We're now ahead of time, but can we just go straight to Nicolas? Cool. All right.